Hi, welcome back to another exciting college algebra lecture for my Math 111 class. My name is Anne-Marie Harden, and I am your instructor in this class. We are going to round out Chapter 1 today with a conversation about transformations in graphs. Some of this you will likely have seen before. Some of it may be new, so let's just take a look and see what we find. Transformations can all be put into three broad categories: shifts, reflections, and scales or scalings. Now, shifts move graphs side to side or up and down. This is like taking your chair and moving it to another spot on a table. Okay? Reflections are, well, it's exactly what it sounds like. It reflects. So when you reflect, if you've got a graph that's all up on top, you reflect it down below. Or you can have a graph that's all over here on the left and reflect it to the right, or vice versa. So it's like putting a mirror on someplace on the on that coordinate plane. Now, scalings are a little bit different. Scalings are stretches. They either stretch a graph out or they squeeze a graph in. And we'll take a look at some of each of these and talk about how it all comes together. The reason why we care about this is because if we know the basic shape of our functions and we can predict how each of these shifts, reflections, and scalings is going to be manifest on a graph, then understanding what the shape of an equation is going to look like when we draw it becomes a whole lot easier. So let's take a look. And as a plug, as we move through this course, and particularly if you're going to go on to Math 112, this is something you really want to get comfortable with. Because looking at an equation, you're going to want to be able to predict what that's going to look like when you graph it, because here pretty quick we're going to start talking about the shapes that specific classes of equations make, and being able to understand translation, shifts, and scales is going to make that work a whole lot easier. So do the work you need to do to make sure this makes sense. We can do this with any graph. We do not have to know the equation of the graph. So we're going to work with this. It's a piecewise defined function, but we aren't going to worry about how it's defined. And we're just going to take these one piece at a time, and I've actually created some Desmos tools to help us visualize this. So I'm going to open up my Desmos. I apologize, I should have done this before I started recording, but I didn't, so give me just a second to get signed in. And open up the graph that I created last night, this one. Okay, now I got a lot of stuff in this graph, but right now what we're going to focus on is what happens if we add something to the end of a function. So this graph here represents my f of x. It's the function we're starting with. And again, we're not going to worry at all about how this thing is defined. I figured that out for last night, but you don't have to. All you have to do is accept that this red line represents my function f of x. Okay? And I want to highlight some points here. So I'm going to put labels on this one, this one, this one, and this one. Okay. And all we are going to do right now is we're just going to add 2 to the end of that. So you see right over here, I've got g of x equals f of x plus a. the important part here is that the thing that we are adding is outside the parentheses. What this is going to do is this is going to impact the outputs of our function. So what I can do is add 2 to each one of these y's. So I'm going to add 2. And so let's just make these points. So I've got a point 0, 1, and I'm going to put a point. I've told you that adding something to the output or to the end of the function is going to affect the outputs of my function. So it's only going to change the y's. So I'm adding 2 to each of my y coordinates. Now, if I'm right, then when I make my a be 2 and turn on this function, look at there. So what happened? Let me show you. Let me take off these points that I put on because they're going to confuse things if I leave them on. But what's happened is adding 2 to the outside of the parentheses, which is what I've got going on right over here. See this right here? Adding 2 to the outside of those parentheses moves my graph up 2 units. All right, let me clean this up a little bit. I'm going to take off these tags, and I'm going to make these points go away because I don't really want them. Whoops, shoot. Brought it back. Okay. All right. So now let's look. What happens if I add 3? Well, if I add 3, my function, I shift up some more. So I'm leaving the original function on here just so we have it for reference. But understand that this is my new function, okay? If I subtract 2, my function shifts down. So the bottom line here is adding something outside of the parentheses, like I've got going here, like this, shifts my functional graph vertically, up or down. It shifts up if we add, it shifts down if we subtract. Okay, now, that's okay. If you have any questions, be sure and ask them. Let's look at another transformation. Let's look at horizontal transformations. Now, horizontal transformations occur when we add something inside the parentheses. So I want you to understand the difference between this, which is g of x equals f of x plus 2, and the plus 2 is inside the parentheses. And this, which is g of x equals f of x plus 2. Here, so think about our factory, our t-shirt factory, okay? We put the fabric in, we get a t-shirt out, and then we do something else to it. We paint a logo on it, okay? That's what this is. This is an adjustment after we've applied the function. This is a vertical shift. What we're doing here, if we think about our function in terms of a t-shirt factory, is we're affecting the input before we ever feed it into the machine. So maybe we tie-dye our fabric, and then we cut it up and sew it. That would be an example. Maybe we embroider an all-over pattern all over our fabric, and then we cut it up and make a t-shirt. So we're making the change before we apply the function. Okay? It's important. So what we're doing is we're adding stuff before we apply whatever we're doing. Let's look at what this does to our graph. So I'm going to turn this guy off, and we're going to take a look at h of x, which is equal to x plus b. So notice the difference. With the b, I'm adding to the x before I apply the function. Let's just make this b2 and see what happens. Adding something to the x before I apply the function actually shifts the function to the left. If I subtract, it shifts to the right. So if I use this as a, okay, so adding 2 inside the parentheses moves us 2 units to the left. Adding 2 outside the parentheses, in other words, after we have applied the function, moves us 2 units up. Okay, so the purple graph, let's spread this out a little bit. Let's make that be 3. And we'll make this guy be 3 just to give us some more space. Okay, the purple graph. So notice, all 3 of these graphs have exactly the same shape. This red guy is the f of x I start with. The purple guy is that same function with plus 2 tacked on at the end. So I put my input in, I've done my stuff to it, and then I've added 3 onto the end. In other words, I've put my fabric into my t-shirt factory, I've done all my stuff, I've made my t-shirt, and then I've sent it to an embroiderer. That's what this purple graph represents. The blue graph, same function f, but this time I added 3 to my x's before I did anything to them. This feels backwards because I added 3 and it shifts to the left. But if you think about the fact that I added before I did anything, then in order to get back to my original, I would need to subtract. So think about that a little bit. Okay. This is like I take my white fabric and I dump it in a vat of dye. And then I go make a t-shirt out of it. Okay? Horizontal shifts, if we add, they shift towards the left. If we subtract, they shift towards the right. Now, see where we're at. This slide just says exactly what I said. So does this one. To graph a function y equals some function f, where we've applied an additive shift to the input, we take the graph of my original function and move h units to the left. The way we do that is we just subtract whatever this number is from the x-coordinates of the point on the graph. So if I went back out here to my graph, let me turn off this guy. Yeah. And so my points that I had put up a minute ago, or a little bit ago, so 0, 1. The horizontal shift is going to affect the x-coordinate. So this is going to be 0. And I'm going to make these actually move. Notice I'm only changing the x-coordinate, because the horizontal shift only changes the x. Okay, you see what we're doing here? I'm just marking the points. Okay. All right, I am not going to beat that dead horse. I think you've got that. So, let me turn off those point labels. Okay. we can have both horizontal and vertical changes going on at the same time. Horizontal changes come from affecting the inputs, the x's, before we apply the function. That's why they are inside the parentheses. Vertical changes originate from affecting the outputs, the y's, after we apply the function. That's why they are outside the parentheses. Okay, I'm going to leave these to you. I just want to talk a little bit about this last one. This last one's got both a horizontal change and a vertical change. Let's go back to my example here. And let's talk about what's happening here. So this guy has got both a horizontal and a vertical. I'm going to put him back where he belongs. So if we start out with my basic function, my f of x, but now I'm going to make a horizontal shift. So I'm going to subtract, let's say I'm going to make a horizontal shift of -3. So this is going to be f of, in parentheses, x minus 3. Oops, this way. So what that means in terms of my Desmos tool here is b is -3. But now I'm also going to make that go, so that I'm going to have a +2, well, -2. Let's go down. So what I actually have here is, I don't know if it'll let me do this. Nope, it won't let me put a label on, I don't think. No. Okay. What I have is f of, in parentheses, x minus 3. And then outside of that parentheses, I'm going to say -4. So what this means for my Desmos tool is that a is going to be -4. So you can see here what I have. If I compare this point, 0, 1, to that same point on my new graph, 3, 3, I've got a change of -4 in my y-coordinates. So 1 minus 4 would be -3, and that's what I see here. And I've got a change of 3 in my x-coordinates. So I compare 0 to 3. So this is how we think about this. If I take 0 and subtract something to get 3, I would subtract -3. So that's my shift, is -3. Okay. If you have any problems with these, so I'm going to, so these are the examples I want you, these are the examples I want you to work through. Yes, you can use your graphing calculator, you can use Desmos. I want to make sure that you can predict at least what's going to happen here. I'd like you to be able to graph these by hand. But I do want you to understand what these shifts are doing. So start with the graph of square root x and predict what's going to happen when we subtract 1 outside the radical, when we subtract 1 inside the radical, and when we add 3 inside the radical and subtract 2 outside the radical. And this is what you should get. So pause the video here. Make sure you know how to do this. If you don't know why you get these things, these graphs that are showing on this screen, I want you to speak up in class or get a hold of me on email or post in the forums. And this is the solution to the rest of those examples. Now we're going to shift gears a little bit. We're going to talk about reflections. A reflection is essentially I multiply by -1 either outside or inside. And you should be able to kind of think about this and see what's going on. So I am going to, I've got this set up here. That's outside the parentheses. And this one is inside the parentheses. Let's start with a reflection outside. So I'm going to multiply by -1 outside the parentheses. What do you think is going to happen? All right, let's see. So to do that on my Desmos tool, I make this be -1. And let's turn on my graph and see what we get. Is that what you expected? If I multiply by -1 outside the parentheses, I reverse the y signs. So I reflect, so I affect my y's. Remember that changes outside the parentheses affect the outputs, in this case the y's. So the point 0, 1 becomes the point 0, -1. The point 2, 3 becomes 2, -3. Okay? 3, 4, or 4, 3 becomes 4, -3. We are affecting the signs only on the outputs. Now, what's a reflection inside the parentheses do? Well, let's turn this off just to keep my... What do we think it's going to do? Turn this one on, and let's reflect on the x's. What happened? We reflected across the y-axis, right? Because we reversed the signs on the x-coordinates. Okay? And yes, you can have both, and if we did that, we would end up with something that was down here. Yes? Okay. We'll do an example of, we'll play with this a bit more in a minute. So, this is the same thing. I want you to do this example. But pay attention as you're doing this to the order of your transformation, because it makes a difference. It's a lot simpler to do these things in a certain order. And remember to talk about domains and ranges, because these transformations are going to affect the domains and ranges, and we will talk about, let's talk through that. Let me open up a different Desmos tool here. And give me just a second to do a little work. We're going to use square root. We'll come back to that other one. Okay. So what I've got here is just a basic square root function. Okay? Now I'm going to start to apply some transformations. And let's go back to my PowerPoint here for a minute. When we've got multiple transformations, the first thing we want to do, let's look at the bottom one down here. The easiest way to think about doing this. Let's look at number 3, because it's the most complex. Actually, let's talk about all of these. So, the domain of the square root function is 0 to positive infinity, right? You can't, if we're restricting ourselves to the real number system, which we are for now, you cannot take the square root of a negative number. So our domain is only the positive real numbers. And what is our range? Our range is also the positive real numbers. Now what happens if I do an internal reflection? In other words, if I make b equal -1. So this is the square root. This is our first example, the square root of -x. So look only at the blue graph. What I've done, let's turn off the red one. What's my domain? Be careful. It looks like my domain is all negative numbers, right? But what do I have right here? I've got a negative sign, right? What I'm saying is that the negative square root of x, or whatever's under the radical, so negative root x, has got to be greater than 0. Because my radicand has to be positive. Divide through by -1. Remember, you got to reverse the radical. And sure enough, it turns out that actually my domain is all negative numbers. So looking at the graph can help us understand our domain. Yes? Yeah. Okay. So what about j? Number 2 here. J of x is 3, the square root of 3 minus x. That's like adding 3 in here. Yeah? So if I go back out here, that's like making my h, my internal adder, be 3. What's going to happen? Shifts the wrong way. Wait. Oh, did it shift the wrong way? It looks like it did. What happens if I undo my internal reflection? Well, that's what I expected, right? So be careful here. I need to understand what's going on. If I don't have, so this reflection reverses the direction of my horizontal shift. Okay. So without that 1, if I do an internal addition of 3, my function shifts to the left. This is what I meant by order of shift is important. We want to do the horizontal shift first, because we know that the horizontal shift moves my function 3 units to the left. Now do your reflection. And what happened was we reversed. Let me do it this way so you can see it. This is going to reverse my graph and mirror it around across the y-axis. So do your horizontal shift first, then do your reflection. Okay, so this is the graph of this guy. Now, what's the domain of this? Well, let's look at that. According to my graph, the domain is all x is less than 3. Where'd that come from? Okay, from 3 minus x has to be greater than or equal to 0. Add x to both sides, and you get that 3 has to be bigger than or equal to x, or my domain is all x is less than 3, less than or equal to 3. Okay, let's do this last one. All right, let me put my original function. So just remind us, we're actually talking about the red function, and we're moving it around. So I'm going to turn everything off. I'm going to make all my multipliers be 1s, and all my adders be 0s. Now this time I've got y equals 3 minus the square root of x. That means I'm adding 3 on the outside, so we'll make my k here be 3. That gave me a vertical shift of 3 units. And I've got a -1 multiplier here. So my a is -1. So it gave me a vertical shift of 3 units up. Okay. And then what? Well, then I just reflected the graph around. Now this may not look like you expected it to. So let's take off my adder. Here's the reflection you were probably expecting. We reflected across the y-axis, and now we add 3. So when you're doing vertical shifts, you want to do the reflection first and then add. This is just like PEMDAS, but kind of reversed, right? But we multiplied first and then we added. It's different than our order of operations. Your graphing calculator knows how to do this, and it can help you. Okay. All right, we are almost done here with this. Now we want to talk about stretches. Okay, let's go back out here to my other graphing tool, the same one that we were using a minute ago. This guy. And I'm going to use my C and D to talk about stretches, because reflections are just special cases of stretches. You get a reflection when your external multiplier is negative. You get a stretch when it's anything other than 1. Let's talk about what's happening here. If I'm going to graph a function that I've doubled, so I'm going to apply, so my g of x is 2 times my f of x. I'm doubling my outputs. This would be like if I made my t-shirt and I live in the future and I put it into a replicator and my replicator spits out 2 of them. That's what I'm talking about here. Okay? So I'm applying a multiplier after I do whatever my function says to do. That will affect only my outputs. So what that means is this point, 0, 1, should become the point 0, 2. Let's see if that is what happens. So this line right here, whoops, sorry. This guy, k of x, is my function that is my f of x multiplied by whatever c is. I turn him on. Now let's see what happens when I make c be 2. Okay. Things got a little stretched. Sometimes this happens when you are rescaling pictures and you only adjust the vertical. Yes, we've all done that. This is how some people try to make themselves look skinnier. Sometimes it works, sometimes it doesn't. Let's see what happened. Let's look at this point right here. We only affected the y-coordinate because we applied our multiplier after our function had done its work. So that means this y should be 2, 6. Yes. And this point should be 4, 6. And yes, it is. And this point should be 5, 10. So notice that when we add, we just pick the shape up and move it vertically. When we multiply by something other than 1, we actually exaggerate one dimension or another. In this case, we're exaggerating the y dimension. Now, what happens if I multiply by, say, 1/2? So let's make C be 1/2. I get a shift, but it's kind of a squishing instead of a stretching, right? What if, so we already know that if C is -1, we get that reflection, yes? What if it's -2? Well, we're going to get that reflection. Then we're going to get that same stretching, just in the negative. This is pretty much the same thing that we got when C was +2. It's just turned upside down. Stretches applied after the function does its work, in other words, in front of the functional parentheses, make things taller. What's going to happen if we apply the function, the stretch, before? Yeah, we're going to affect the inputs. This is like doubling my fabric before I make my t-shirt. I get a whole different object, a whole different output, right? Okay, let's see what happens. If I multiply by 2, things get squished. My point 2, 3, but they only get squished in the x, right? So what happens to my point 2, 3 here? It becomes 1, 3. My point 4, 3 became 2, 3. And this point 5, 5 became 2.5, 5. So I divided all of my x's by 2. Those internal shifts, stretches, modifications are always going to feel a little backwards. If I multiply inside, then I end up with a squish. If I divide, so let's make my D be 1/2. I ended up with, oops, sorry, a stretch, right? My point 2, 3 moved to 4, 3. My 4, 3 moved to 8, 3. And my 5, 10 moved to 10, 5. I'm affecting the x coordinate, but I'm affecting the x coordinate with the inverse of whatever my modifier on my function is. Okay. This just says what I vocalized to you, and this is the horizontal shift. And I want you to play with the square root function and make sure it makes sense to you, what's going on here. Make sure you understand all of these. Bring any questions you have to class. And this is kind of the overall summary. So this is your takeaway message. Make sure that you can do all of these things, and you'll have to practice them. That's the only way to do this. So to graph a function g of x, which is equal to some number a times some other function f, where I've got internal shifts of b times x plus h plus k. We first subtract h from the x coordinates of all of the points. This will give us our horizontal shift. Then you divide those shifted x coordinates by whatever your internal multiplier b is, and this will give you the horizontal scaling, but may also give you a reflection if b is negative. Once you've taken care of your internal horizontal adjustments, again, do your horizontal shift first, then accomplish any horizontal stretching by doing the division. Now we'll apply the external adjustments. So first, apply your external multiplication by multiplying each of your points by that number A, and then add your external shift, your K, to each of those points. So, internal shift, internal stretch, external stretch, external shift. So shift, stretch, stretch, shift. Start from the inside and work your way out. Let's take a look at this. I know we're going long. We are almost done. But I want to demonstrate this for you. So write down this function. We're going to take a look at this function, this guy, this f of x. I don't need you to worry about the equation for this. I've got it graphed. You don't need to worry about what the equation is. I want you to be able to take this graph and do these adjustments to it. So we're going to take 4 minus 3 times f of 1 minus 2x. And we're going to divide the whole thing by 2. Now, before we do anything, we're actually going to rewrite this a little bit, because we're going to rewrite this as with this 2 distributed through. So this is a common function, a common denominator. We're going to split it out. And 4 divided by 2 is 2. Come on, give me my pen. Pen. 2 minus 3/2 of f of 1 minus 2x. We can't do anything to the stuff that's inside these parentheses. But we can take this 4 and divide it by 2. And we can take this 3 and divide it by 2. And that's what I did here. So now what do we have going on? We've got a horizontal shift of 1 unit to the left, a horizontal stretch of -2, a vertical stretch of -3/2, and a vertical shift of +2. Okay? This 1 gives me a horizontal adder of 1. This multiplier gives me a horizontal stretch of -2. The next thing we'll do is this vertical stretch of -3/2. And then we'll do a vertical shift of +2. So let's take a look at that. Okay. So I've marked some points on my graph. All right, now, remember what we're doing. What's the first thing we do? We do the horizontal shift. So the first thing we do is the +h. And we said our +h is 1. So I'm going to make h be 1. Remember, that moves all of my points 1 unit to the left. All right? The next thing that we do, and I'm just doing points right now. We'll turn on the curve in a minute. But I'm just using Desmos to move my points around. You can do the same thing by hand, okay? The next thing we're going to do is, remember we have a times -2x. So what we have inside my parentheses is 1 minus 2x. If we look up here, what that means is h is 1, b is -2. So let's make b be -2. What's that going to do? It's going to crunch things, right? And turn them upside down. And yes, it did that. Okay? It looks weird. It looks weird because it's also shifted. So it doesn't turn them upside down, actually mirrors them left to right. And on this function, it's symmetrical. So, but if you look, I color coded. So my purple point that started out on the left here, it moves. So let's just move my points. So see everything moving? And they swapped sides. So they crunch in, and the points that were on the left moved to the right, and the points that were on the right moved to the left. Okay. So we've done our internal. So we've done shift, stretch. Now what's next? The external stretch. And my external stretch is a -3 divided by 2. So -3/2. And here on my little key, that means A needs to be -3/2. Oh, wait. Okay. Sorry, I lost my slider. So let's do it this way. -3/2 is -1.5. There, I like that better. Okay, that's my vertical. So my vertical shift took all of my y coordinates and multiplied them by 1.5. But it was all of my y coordinates relative to what I had in the last step, which actually were my originals, right? So if we put my A back to 1, notice to this point I hadn't moved anything up and down. I had only affected the horizontals, so only the x coordinates. So that means that this point here that is at the point 0, 3 should become what? I'm going to multiply it by -3/2. So it should become 3 times -3/2, 9/2. So 4, -4.5. Yes. Now, the y coordinate is affected because we already, or the x coordinate's been affected because we already did our horizontal shifts. The last step now is to do our horizontal shift, not our stretch. We just did our stretch. Now we're going to do our vertical move, which means add 2. So this k becomes +2. So all I've done so far is draw my points. If I did everything correctly, when I turn on this guy, which has just got my function with all of that stuff built into it, then those curves will go through, that curve will go through those points. Shall we see? Hey, I like it when that works. Okay. So I want you to be able to understand how we did this and what direction everything moved. Desmos can help you. Practicing is how you do this. All right. I will see you all in class. Post any questions that you have to the forum, and we'll talk it through when we get together again. Have a great day and do good math.